Okay, so hello and welcome back. So in this video we want to talk about types of functions. There is a couple of types of functions that we will study in this section. So about the types of functions. So basically what we have is that, so basically if you have read the chapter in class 11, there was a chapter in class 11. I will show you where that is, and then hopefully some, of course, well, we didn't actually do a review of that part in this chapter, but if you go to basically the roadmap of all of these courses, if you go to class 11, and you can see that relations and functions, there is a chapter in class 11 that talks about relations and functions. In that, basically we talk about a few concepts, like for example we of course talked about the notion of functions, some special functions like the identity function, like the constant function, like the polynomial function, the rational function, the modulus function, the signum function, etc. And we also talked about the graphs, and also addition, subtraction, multiplication, and division of functions we also talked about in that chapter. If it's required, we will go back and do a review of them. Otherwise, I don't think that really that's required right now. Now, what we want to do here basically is talk about different types of functions. Let's say that you have basically some different functions. Let's say that you have, for example, 1, 2, 3, and 4. Let's say that this is a set that has been mapped to another set, A, B, C, D, E, and F. And the mapping in this case is basically something like this. And remember that these are these are functions and not relations. Of course, a function is a type of a relation, but these are strictly functions, meaning that we said that okay, so basically we said that if you have this type of situation, for example, you have a set, for example, you have some set A over here, and you have some set B over here, and suppose that you have, for example, A1, A2, A3, and A4 here, and you have B1 and B2 and B3 over here as the elements of these two sets. Then if this element is mapped to this element, and if this element is mapped to this element, and if this element is mapped to this element, and this element is also mapped to this element, then this is called a function. Meaning that you can say that and you can call it, for example, the relation, you can call it F for a function. Meaning that you can say that basically a function is a type of relation in which every element of set A, every element of the set A, meaning that, as you can see, all the elements in the set A have been mapped to something, right? Meaning that there is no empty elements here that has not been mapped to some element in set B. So we say that every element in set A has a distinct image in the in the set B. So basically you can say that if every element in A has a distinct element in B, right? So what that means is that first of all, every element is A has been mapped to something, and every element in A has a distinct element in B, meaning that you can say that the image of A1 is B1, the image of A2 is B2, the image of A3 is B3, the image of A4 is B3. That's a function. On the other hand, you could have this type of situation where this is A and this is B, and you have, for example, A1, A2, and A3, and you have B1, B2, and B3, and then this element has been mapped to this element, and this element has been mapped to the same element, and this element has been mapped to this element. You can see that in this case, of course, every element in A has been mapped to something in B, but the images of A1 and A2 are not distinct, meaning that A1 and A2 have the same images in B, which means that this is not a function, right? So I'm sorry, no, which means that basically what that means is that basically every element right here has been mapped to the, but then well, of course, every element here, again, I made a mistake here, I apologize. Every element here has, again, a distinct image in B. But suppose that you had some situation like this. I did make a mistake here. Suppose that you have some situation like this, meaning that you have B mapped to these two elements, and this element has been mapped to this element. Now, let's say that there's a B4 over here, and this element has been mapped to this one, so we have no empty elements here. But then the problem here is that we said that every element in A is supposed to have a distinct element or image, basically, or image in B, meaning that, as you can see right here, the element A1 has been mapped to two elements in here, B1 and B2, right? So the element A1 has been mapped to B1 and B2, which means that basically A1 in this case has more than one image in B. So that means that this is not a function. And as you can see, if I call this relation, if I call it an f, then you can say that, for example, f of A1 here, there is no way to know what that is, because it could be B1 or it could be B2, right? You don't know what that is. But over here, what happens is that basically in this particular case, in this one, you know that f of A1 is equal to B1. F of A2 is equal to B2. And f of A3 is equal to B3. And f of A4 is equal to B3. So it's possible in each and every one of these cases to decide what is the image of each and every element of A, what is the image of all of those elements in B? And so that means that this is a function. But of course this is not a function because there is no way to decide what is the image of A1 in the set B, right? Now when we come to the type of functions, there are basically a few types of functions that we will mention here, and those are basically, suppose that you have, for example, some situation like this, meaning that you have 1, 2, 3 and A through F, and 1 has been mapped to A, and 2 has been mapped to B, and 3 has been mapped to D, and 4 has been mapped to C. So as you can see, all the elements over here has been covered. There is no empty element here. And every element in let's say in X1, every element in X1 has a distinct image in X2. And of course you can see that E and F are the images of no element in X1, but that's not a problem. And we call this a function F1, for example, or a relation F1, right? So that is one type of situation that you could have. Another type of situation that you could have is that you could have something like this. For example, you could have 1, 2, 3 and 4. You could have 1, 2, 3 and 4, and you have A, B, C, D, E and F, right? So you could have that, and 1 and 2 have been mapped to B. So 1 and 2 have been mapped to B, and 3 has been mapped to C, and 4 has been mapped to D. So we can have this type of situation as well. Call it, for example, F2. Call this, for example, X1 and X2. And you could have another type of situation where, for example, you have 1, 2, 3 and 4. And then over here you could have A, B and C. So this is another set, for example, X1 and X3. And then 1 and 2 have been mapped to A. And 3 has been mapped to B, and 4 has been mapped to C, and this is called F3. You could have another type of situation where you have 1, 2, 3 and 4. 1, 2, 3 and 4, and you have A, B, C, and D over here. And so suppose that 1 has been mapped to B. Suppose that 1 has been mapped to B, and 2 has been mapped to C, and 3 has been mapped to A, and 4 has been mapped to D. And call it, for example, F4. And this is X1 to X4, right? Now, if we take a look at, let's call it, for example, let's call this number 4. Let's call this number 3. Let's call this one number 2. Let's call this one number 2. And let's call this one number 1. Now, these are basically some different types of functions that you could have, and we will now give them some names so that we can refer to these different types of functions in the future. And depending on which type of function you have, then Of course, you can see that the properties are a little bit different, although all of them are actually functions. So basically in this figure that we have here, we can observe that the images of distinct elements of x1 under the function f1 are distinct. So I repeat that. We can see that basically the images of the images of distinct elements of x1, 1, 2, 3, and 4 under the function f1 are distinct, right? But the image of two distinct elements 1 and 2 of x1 under f2 is the same. So but the image of, as you can see over here, the image of two distinct elements 1 and 2 of x1 under f2 is the same, right? Which is basically, in this case, the image of 1 is B, the image of 2 is also B. But the images of all of these elements are distinct, A, B, C, and D, 4 different distinct images. Moreover, basically there are some elements like E and F in x2 which are not images of any elements of x1 under f1, meaning that these are not the images of any of the elements of x1 under f1. While all elements of x3, for example, are images of some elements of x1 under f3. While all images of x3 are the images, while all the members of x3 are the images of the members of x1 under f3, right? So based on what you can see here, basically then we can basically come up with a couple of definitions. Now, in order to make this simpler for us, I'm going to make a screenshot here. Make this probably, for example, 75%, so that everything fits together here. And I'm going to make a screenshot here. Okay. So I need to go to some other. Okay, come on. Okay, so as definition number 5, we can say that function f, the function f from x to y is defined to be 1, 1 or injective called basically 1, 1 or injective if the images of distinct elements of x distinct elements of x if the images of distinct elements of x under f are distinct, under f are distinct. That is for every x1, x2. That is for every x1, x2 belonging to x, f of x1 is equal to f of x2 implies that x1 is equal to x2. So what this means is that for every x1, x2 belonging to x, is if f of x1 is equal to f of x2, that implies that x1 is equal to x2. That means that if f of x1 is equal to f of x2, the only way that can happen is if x1 and x2 are basically the same elements, right? Meaning that x1 is equal to x2. Or in other words, you can say that the function is a 1-1 or a 1-1 function or an injective function if the images of distinct elements of x under f are distinct. And as an example, as an illustration for this part, what we can point out to is the functions f1 and f4 in the illustration that we just had. Okay, so basically we said that basically a function f from x to y is defined to be 1-1 or injective if the images of distinct elements of x under f are distinct. That is, for every x1, x2 belonging to x, f of x1 is equal to f of x2 implies that x1 is equal to x2, meaning that if f of x1 is equal to f of x2, then the only way that can happen is that if x1 is equal to x2, meaning that x1 and x2 are the same elements. And then otherwise you can say that basically f is called many 1. Otherwise, basically f is called many 1. So basically we have two ideas here. We have the idea of a 1-1 or injective. You have the idea of a 1-1 or injective, and opposed to that idea, you have the idea of a many 1, right? Now, we had basically we had 4 illustrations here, and in order to show you what I mean by 1-1 or injective, so the functions f1 and f4, number 1 and number 4 are 1-1, and the function f2 and f3 are many 1, meaning that if you take a look at this illustration, you can see that basically in this case, for example, all of the elements of x1 have distinct elements in x2 in this case, for example, and all of the elements of x1 here have distinct elements in x4. So in these two cases, you can say that basically f1 and f4 are 1-1 or injective. But then in these two cases, in case 3 and 2, what you can see is that basically these two elements 1 and 2 are mapped to the same element, meaning that these two distinct elements don't have a distinct image, don't have two distinct images in, for example, in x3 here, or in this case, for example, 1 and 2 don't have a distinct image in x2 here under f3 and f2. And so you can see that, so this, because more than one has been mapped to one element here, this is called many one. And again over here you can see that because more than one element in x1 has been mapped to the same element in x2, this is again called many one. Now 1 1 is, or injective, is basically a very simple idea, and that is that basically one element has been mapped to another element, one element has been mapped to another element, one element has been mapped to another element, and so on and so forth. So that is 1 1, 1 1, many one, right? Now, the another definition that we have here is definition number 6. Is definition 6, and that is a function f from x to y. Function f from x to y is said to be onto or surjective. Is said to be onto or surjective. Is said to be onto or surjective if every element of y is the image of some element of x under f. If every element of y is the image of some element, some element in x under f. That is for every y belonging to y. That is for every y belonging to y, there exists an element x in x. There exists an element x in x such that f of x is equal to y. Such that f of x is equal to y. Okay, so we said that basically definition number 6, we said that the function f from x to y is said to be onto or surjective. So these names, we need to learn them, of course. If every element of y is the image of some element of x under f, that means that basically, that simply means that basically every element of y has been covered in that, under that function, meaning that, for example, as you can see here, every element of y, or x3 in this case, has been covered. No element of x3 is empty here. In this case, again, you can see that basically every element of x4 is the image of some element in x1. But in these two cases, as you can see, there is E and F over here that are not the images of any of the elements of x1. Again, over here, E and F are not the images of any of the elements of x1. And so you can say that the function, for example, the function f3 and f4 are onto, and the functions f1 is not onto. So f3 and the functions f3 and f4. So if you think about f3 and f4, which is basically these two functions, these are as we mentioned before, these are onto, or basically these are onto or surjective. These are onto or surjective because as you can see, every element of x3 over here is the image of some element here. Again, over here you can see that every element of x4 is the image of some element here, but that is actually not the case here. So then you can say that the function f3, which is this one, and f4 are onto, and the function f1 and the function f1 is not onto, as element e and f in x2 are not the image of any element in x1 under f1, for example. So this is not onto or surjective. Moreover, you can, as a remark, you can say that the function f from x to y is onto or basically surjective, if and only if range of f is equal to y. Range of f is basically equal to y. So what that means is that so basically when we talked about functions, we said that we came up with basically three names here, and the names were domain, we had the range, and we had the codomain. We had the codomain, meaning that, for example, if you have some function, for example, let's say that you have a, b, c, and you have, for example, 1, 2, 3, and 4 here, and let's suppose that, for example, a is mapped to 1, b is mapped to 2, and c is mapped to 3, you can see that 4 is not the image of any of the elements of x1, for example. Let's call this, for example, x. Let's call this, for example, x and y. Under f, basically 4 is not the image of any of the elements of x. So then you can say that you can say that, of course, this is a function. You can say that this is a function, but and of course it's a 1-1 function, because every element of x has a distinct image in y, but it's not an onto function, or it's not a surjective function, because there is this element 4 here that is not the image of any of the elements of x, right? So now in this situation, you can say that basically this set A, B, and C, these three elements A, B, and C, you can call it the domain of F, meaning that all the elements that have been mapped to some element in y, or all the elements that are pre-images of some element in y, right? And that happens to be the set X itself, right? Now, moreover, you can see that basically these elements 1, 2, and 3 are the set of these elements. You call it the range of F, and you call only 1, 2, and 3 the range of F. 4 is not a member of this set, because 4 is not the image of any of these elements in X. And so, as you can see, the sets 1, 2, and the set containing 1, 2, and 3 is just a subset of Y. This is a subset of Y. But then in the same situation, you can say that this set containing 1, 2, 3, and 4, which happens to be, of course, the set Y itself, is called the codomain. Is called the codomain of Y. The codomain of F. Is called the codomain of F. And so basically the whole set Y is called the codomain of F, and it doesn't really matter whether all the elements of Y are images of some element in X, even if, for example, there is some element in Y that is not an image of some element in X. The whole set Y is called the codomain of F. Now, as you can see here, basically the range, which is 1, 2, 3, is a subset of the codomain, right? Now, basically, as a part of this remark, what we said was that f as a function from x to y is onto or surjective if and only if means I double f, which is a biconditional, which is basically f as a function from x to y is onto or surjective if and only if the range of f, which is basically in this case, for example, only 1, 2, 3 and doesn't include 4, the range of f is equal to y, which is, as you can see in this case, that is not the case. The range of f is not equal to y here. The range of f is 1, 2, and 3, and y is actually this set over here which contains 1, 2, 3, and 4. So 4 is missing here. So you can say that in this particular case, you can say that the range of f is not equal to y, and therefore f is not an onto function. And one more thing that you need to pay attention to here is that here we are saying if and only if. So this is a bicondition, meaning that if you have, what that means is that you can say that f as a function from x to y is onto if basically this is the case, and also you can say that the range of f is equal to y if and only, I'm sorry, let me write it down over here. So the remark that we had was that f as a function from x to y is onto if and only if range of y is equal, range of f is equal to y. Range of f is equal to y. So since I'm using if and only if here, that is basically I double f, which is a bicondition. So a biconditional, if I take this basically this element over here, this statement over here as for example some statement q, and if I take this statement as statement p and statement q here, what this means is that I'm saying that p if and only if q, right? Which basically, what the meaning of this statement is basically p implies q and q implies p, right? So, and we have already talked about basically these are conditionals. These are called conditional. This is called a conditional. And this thing over here is called a biconditional. This thing over here is called a biconditional, right? So a biconditional is a two-way conditional, meaning that P implies Q and Q implies P. But then when you have a conditional, what that means is that P only implies Q, but then Q doesn't imply P. But since you have a biconditional, what that means is that basically P implies Q and there is an and here, and also Q implies P, meaning that Q implies P, and you know what that means is that, and the meaning of basically the statement P implies Q, or if I write it this way as P implies Q, meaning that P is true, only if Q is true. And when I say Q implies P, what that means is that Q is true only if P is true, right? Which means that if I want to show that basically P implies Q is true, basically if this has to be true, if this statement has to be true, then P has to be true, has to be true, and also Q has to be true, right? So that's basically the meaning of these conditionals. Now over here what I'm saying is that basically this statement P, which is f some function from x to y, is unto if and only if the range of f is equal to y, which means that this statement P is true if and only if statement Q is true. So then what that means is that again, basically that means that P implies Q and Q implies P. Now P implies Q means that, if I want to write it down in English, what that means is that f as a function from x to y is unto or I can write it this way. I can write it f as a function from x to y is unto implies that the range of f is equal to y. That's how I can write it. F as a function from x to y is unto implies that the range of f is equal to y. Another way of writing the same thing, now I don't want to confuse you here, another way of writing the same thing is that if f as a function from x to y is unto, then the range of f is equal to y. Then the range of f is equal to y. And you can do the same thing for the other part as well. So this was for P implies Q. You also have Q implies P because it's a biconditional. It's a double-headed arrow, right? So Q implies P. So Q implies P means that basically the range of f is equal to y. The range of f is equal to y implies that f as a function from x to y is unto. right? The same statement I can write it in English or in words as if the range of f is equal to y, if the range of f is equal to y, then f as a function from x to y is onto. So that's the meaning of all of this. And when I say if the range of f is equal to y, then f as a function from x to y is onto, what that means is that if this statement is true, then this is necessarily true. This has to be true, otherwise this cannot be true, right? And we have talked extensively about these kinds of implications, so I suppose you hopefully understand them. And we have one more definition here. We have one more definition here, which is definition number 7, which is definition number 7, which says that a function f from x to y, a function f from x to y is said to be 1, 1, and onto, is said to be 1, 1, 1, 1, and onto. So this is important. This is both 1, 1, and onto. Or bijective, or you can call it bijective, or bijective. This is also called bijective if f is both 1, 1 and onto. 1, 1 and onto. So this is simple to understand. If you have understood basically 1, 1, and if you have understood onto, then basically if the function is both 1, 1 and onto, put both of them together, then you can call it a bijective function. And then basically a function f from x to y is said to be 1, 1 and onto, or bijective, if f is both, well, 1, 1 and onto. It's very simple. And basically the function f4 that we had here is actually an example of that. You can see that basically the function f4 here is of course 1, 1. Every element here has its own distinct image in x4. That means that it's basically 1, 1, and it's onto because every element of x4 is the image of some element in x1. So therefore you can call the function f4 as 1, 1 and onto, which is also called a bijective. So in the next video we will talk a little bit about, we will take a couple of examples. There is example number 7, 8, 9, 10, 11, 12, and 13, and then we have a couple of exercises. So I'll see you in the next video. Thank you.